Welcome back. Now we're going to look at the theory behind section 16.7, change of variables. But you know what? We've really seen it already. This is just the Jacobian determinant that we've computed for the polar transformation and spherical transformation and cylindrical transformation. But since those were basically all the same kinds of transformation, I wanted to focus on how we can generalize the idea and figure out how it relates to geometry, going back to relating areas and cross products. So let me dive down a little bit here. Our goal overall is to be able to convert an oddly shaped solid or region into something that's simpler geometrically. You can imagine it as if we have this blob in Play-Doh, some oddly shaped solid, and we want to deform it in somehow, continuously deform it in a way that returns it down to a nice, simple shape. So let's remember what we did with the Jacobian back in polar coordinates. We computed the conversion factor. This is way back in the section on chain rule. And then we formed this inverse of determinants of these partials, just like how we can form the inverse of the derivative du dx in the chain rule. And computing out the pieces, we get r. And because r is a non-negative value, we don't have to take the absolute value of it. It's already done. But in general, we want to look at the absolute value of this Jacobian determinant. Now we're going to generalize this to variables u, v, and w as new x, y, and z. And can we do this? Yes, we can. In fact, the form of the transformation is identical to what we just did in polar, cylindrical, and spherical coordinates, except the value for the Jacobian differs based upon our transformation. The form of it can be done in the same way. But let's look at this geometrically. In 2 dimensions, let's work with some new variables we want to transform into u and v, and we want to write our x and y in terms of them. And let's think about how a small change in u and v can be linearized into changes in our x and y dimension. So for that, I'm going to transfer over to a page I found, description of. And this shows a transformation between a nice shape or region in u and v space to a rather complicated shape or region in x and y space. But if we zoom in small enough, it can look like a little parallelogram. And so this dx and dy vector we're going to focus on are not necessarily in the x and y direction, which is ironic. They are kind of tilted a little bit, but they're used to form the change in area, the little pieces of area that we're adding up. And they come from very nice changes in u and v, little pieces of du dv. And so what we're going to do is take this du change, which is going in the I hat direction, and dv as a vector going in the j hat direction, and then multiply them using the column notation into the matrix to get the 2 vectors x sub u du and y sub u du, one vector there, and then x sub v dv and y sub v dv. Now let me translate this over into a row form, a shorthand row form, so it looks a little bit more familiar. We can write the change in x, or let's just say it the x change vector as x sub u du and y sub u du. This is basically the changes in terms of u. and x sub u and y sub u are the conversion factors, much like r sub x and theta sub x, only reversed. So this is the change occurring because of u. And then dy is the change vector that's kind of like in the y direction. That's due to the change in v. And then when we form that little piece of area, we're finding the absolute value or the magnitude of the cross product of those two vectors. And that represents the area of the parallelogram. And so let's compute out that cross product. Back in the day, we'll just throw on a little zero there, and then we have our I hat, our J hat, and our K hat, and we can compute the cross product really nicely. Notice that in the I hat direction, we get 0 minus 0. I'll write that out in a different color, pink. We get 0 minus 0. And then in the J hat direction, there, I'll erase that. Just not use a color. I will use a spotlight. There we go. 0 minus 0. And for J hat, we get 0 minus 0 going the opposite direction. And then finally for K hat, we get the product down minus the product back up. So let's write that down here. We notice that there's a common du dv, so we can factor that out. And we're taking the magnitude of this vector, but there's only one component, so it's just the absolute value of that piece. I write that as an absolute value. Come down there and give it absolute value bars instead of parenthesis bars. And then that absolute value is a difference of products. Notice there's an x here and there's an x there. Let's group that in terms of the first row, x sub u, x sub v, and then a y sub u, y sub v, y sub u. There we go, reordered. And so we have a 2 by 2 determinant for just the partial derivatives, taking the absolute value of that, times du dv, and we call that the absolute value of the Jacobian determinant times du dv. There it is. So that Jacobian determinant is actually the area of the parallelogram formed from little changes when we linearize our relationship between x and y to u and v. Now, the good news is, if we deal with linear relationships, then it's exactly a parallelogram, which is kind of cool. Oh, but by the way, notice that our form, here I'll clear the annotations, our form we just computed here is a little bit different than the form we computed previously for the Jacobian. Let's go back up. Before we had u in terms of x, u in terms of y. And what that tells us is not that we did it wrong, but that there are two different ways to compute the Jacobian determinant. One is the inverse form that we saw before, and the other is a direct form. And these notations right here are a way to summarize how the partials are taken. So we call this the inverse form, where we write the Jacobian of u, v, and w, the new variables, as partials of the new variables in terms of the old variables, all of the partials of the new variables, in terms of the variables, and then inverted or reciprocated like this, where each row is a new variable and each column is a partial in terms of an old variable, whereas the direct form has this ratio of partials notation to denote the matrix with a determinant of a matrix of partials of each of the numerator variables in terms of each of the denominator variables. And here we have that form right here. And that's what we found from simplifying the area calculation. We found the direct form. Sometimes the direct form is easier, sometimes it's harder. So we'll be able to use both those, but keep that in mind. Okay, now I want to do one example just to flesh out this idea and see some of the beautiful properties when we have linear transformations. So our first example, I want to find the area and center of mass of a thin plate with constant density bounded by the ellipse x over a squared plus y over b quantity squared equal to 1 for x and y greater than or equal to 0. So this isn't the full ellipse, this is actually a part of the ellipse. Let me draw a picture of that so we can see it. So we have something like this. We want to draw an ellipse on top of it. Here is a circle, and we're going to stretch it out a little bit. Now, what we're actually computing is based upon values of a for the x and b for the y. So let's write that down. This will be a and minus a. This will be b and minus b for the y-axis. And what we're actually computing is the area and center mass of this region over here in the first quadrant. Okay. So let's look at what we have to work with. Now, since it's an ellipse, you can imagine that as being a shape that we could squish. We could squish this ellipse into a circle. And to do that, we're really going to replace the x over a with a new variable, u, and the y over b with a new variable, v. Now, how do I know that that squishes it into a circle? Well, if I do that, I get the equation u squared plus v squared equals 1. It's so close to a circle, why not make it a circle? And since u is x over a and x is positive, then u must be positive or non-negative. And if v is y over b and y is greater than or equal to 0, then v is greater than or equal to 0. So we have the bounds translated over really nicely. And so we can compute the Jacobian determinant. And we can actually use either form, the inverse form or the direct form, because this is such a nice relationship. It's very easy to switch in between solving for u and v in terms of x and y, or solving for x and y in terms of u and v. So let's look at it. If we take the u and v partials in terms of x and y, that's where we get 1 over a, 1 over b. It's our diagonal entries, 0 because u does not determined by y, and 0 here because v is not determined by x. Similarly, taking the x and y partials of u and v, the u partial of x is a, v partial of 0, the u partial of y is 0, and the v partial of y is b. Very nice. And we can compute out the results getting a times b in each case. Okay, so first, note that Jacobian is a constant. Because we have constant multiples, we get a constant Jacobian. There's no nonlinear powers of u and v, so that there's no function of x or y or u or v that pop up. Unlike with polar coordinates, we had r's and thetas combined together to give us the Jacobian equal to r. Here we just have constants. It's very nice. So notice that if we have constants and constant multipliers specifically, we can scale those or factor those out of all the integrals. So that is one of the most helpful things. And specifically, Jacobian will always be constant, even when we have other linear combinations. Like say that u is a combination of ax plus by plus cz. That is still a linear combination. We can still integrate through that by breaking into 3 integrals and factor the a's and the b's and the c's out of each separate piece. So we can do lots of factoring, lots of beautiful algebra here. And let me clear my annotations before we go on. So now that we have the idea figured out, let's look at computing the area. We start out with this nasty form. I wrote it out just for fun. It's not pretty, right? That is the integral form for our ellipse, our piece of the ellipse. You may say, it's not that bad. I'm like, yeah, it is actually. It's quite bad. You're basically integrating this square root function, and that b is multiplying in there. So it's, make sure you know that the b is actually multiplying the whole thing. Yeah, I guess I can't really change it. It's a big B times the whole square root, whatever. Okay, so big picture is that it's the double integral dA. So we translate that into the double integral of the Jacobian determinant times du dv, or dv du, either or. We translate it into the ordering dv du, multiplied by ab, and we get this somewhat less complicated form. And we recognize the circle, right? We see that this is the form where u squared plus v squared equals 1, and it's the top quarter circle. So we immediately translate that integral into polar coordinates. And we use the same polar transformation. It's like nothing, it's like the u and v never happened, right? We just factor that ab out, and then we transfer into polar, integrate over that quarter circle from 0 to 1 and 0 to pi over 2. Now we don't actually have to integrate here because we know what the area of a circle is, and we know what the area of a quarter circle is, just 1/4 of pi. This is a circle of radius 1, right? Quarter of the unit circle. So we get AB pi over 4. And see how that is just the Jacobian times the area in the UV space, the pi over 4. When we have a linear transformation, the Jacobian being constant is simply multiplied by the area in that new space. So if we can squish this shape into a circle, then we can use the properties of this circle and relate it back, as long as we can squish linearly. Okay, now centered mass. A little bit more complicated. We start out with the integral of x dA because our x bar is actually equal to x average, isn't it? Just disguised as x average here. And so we calculate our x average over the area, and then we translate over into u, right? That is a times u, and we write our Jacobian, translate into the UV space, and notice that if we factor the a out, we have u times the Jacobian piece over the area, and those two Jacobians will cancel. Let me write this area integral out on the bottom, just so it's abundantly clear what's happening here. The The area in the bottom is the double integral of AB, the Jacobian, times dv du. And so if we cancel out the AB's and we factor the A out, we have the double integral of U dv du over the area in terms of the UV space, which is simply A times U bar. Whoa. So if we know what the center of mass is, or the centroid in this case, I'll write that as AU average, which equals AU bar. So if we know what the center of mass coordinate is in the UV space, which we've done this a few times, we could probably figure that out, then we simply multiply by A to get the x center of mass. But let's work through it as if we don't remember. Go back to this form of the integral, keeping that area the same in the bottom. We translate into polar coordinates using u as r cosine theta and v as r sine theta, basically treating u as a new x and v as a new y. Factoring out the constant Jacobian and the constant a, we get this a squared b on the outside. And then we integrate cosine, we get sine. Evaluated, we get 1 minus 0. We're integrating r squared, we get r cubed over 3. Evaluating, we get 1/3 minus 0. And that gives us the ratio of two fractions, which is the multiplication of first times the reciprocal of the second, a squared b over 3 times 4 over ab pi from the area calculation up there, giving us 4a over 3 pi, which, if you remember, is a times 4 over 3 pi. That was the center of mass location we had on an upper unit semi-circle, right? That's the y bar value we had before. And so we've seen that before. It's not unexpected, and we could use them. If we have that information done already, we can utilize it to calculate this new value as we change over to an ellipse. Y bar is similarly calculated. We go through it and remember that using the same steps, we could cancel out the Jacobian and show this is actually b times v bar. But going through the integration steps, we integrate out and we get a 1 in this case, 0 plus 1 and 1/3. It's very similar form here, except it's b. B times 4 over 3 pi. Now, why is this important? Well, because x was a times u and y was b times v. Then, if we know what u bar and v bar are, they happen to be 4 over 3 pi, following the pattern we had before, then x bar is just a times that, and y bar is just b times that. So a nice pattern here, and that works for any ellipses. We've restricted it over this first quadrant, but for any a and b value. So here's some takeaways from that example. The area and volume of a linear transformation has the following property. As long as you have a linear transformation between the old variables x, y, and z and the new variables u, v, and w, the Jacobian determinant is constant. And because it's constant, we can factor it out of the volume or area integrals, which means the volume in x, y, and z space is the constant Jacobian times the volume in u, v, w space. We saw that with area, right? The area in the xy space is the constant Jacobian times the area in the simpler space. So basically what we're saying is the measurement, volume or area, of this weird shaped thing we have, if it's a linear transformation, it's simply the Jacobian we compute times the simpler volume or area geometrically, which honestly we can usually figure out without any integration required. And even more importantly, the center of mass and centroids from linear transformations can be calculated directly from the linear relationship. For example, if we have u is equal to ax plus by plus cz, a much more complicated linear relationship, we can write the relationship that u bar is equal to ax bar plus by bar plus cz bar. The relationship between centers of mass is the same as the relationship between the variables. How? Let's look at it. We dive in. Here, we'll throw it all in. We'll throw the density function to get our mass. Everything is there. So if we compute the u bar, that's the moment of u times the mass function, the density function. I'll leave it in x, y, and z. You could think of it in terms of u, v, and w translated. Divided by that mass. And then we multiply top and bottom by the Jacobian, which is constant because it's a linear transformation. And once we have that Jacobian in there, we can move over into the x and y and z space, get our dv piece, and then translate our u into the x, y, and z space. That allows us to rewrite the bottom as our mass and our mass in the x, y, z space, where this one is the mass in the u, v, w space, right? Weird piece there. And then we can break up this one integral of 3 pieces added together into 3 integrals. And because they're each multiples of x, y, or z, we can factor out those multiples, and we're left with the integrals of x times the density function over the mass, that is x bar, integral of y times the density function over the mass, that's y bar, and the integral of z times the density function over the mass, that's z bar. Each one is scaled by the corresponding component, either a, b, or c, that's in the linear relationship that makes up u. So in the same way, if we have a linear relationship for u, v, and w in terms of x, y, and z, or in reverse for x, y, and z in terms of u, v, and w, the center of mass coordinates follow the same relationship, the same equations, the same linear equations. Okay, so I will save this so we have that idea wrapped up, and then we'll move on to some examples.